3D graphics is really just vertices and edges. Visually, it's even simpler. Vertex isn't something you draw, an edge, that's just a line. Draw line might not look like much, but don't forget that all 3D models in their wireframe form are just a bunch of lines. I have this Rubik's Cube. For illustration, we have a front face, back face, sides, up and down. All of them are squares, so let's start by drawing a square. Just 4 lines. Let's say this is the front face. If I position my Rubik's Cube like this, you can see that it is exactly what we programmed. How cool is that? But what if I do this? Well, you might think you just draw 2 more squares, right? No, unfortunately, real-life squares don't look like perfect squares on the screen in this configuration. Rotation ruined everything, so let's take a look at how rotation actually works. Imagine I have a pivot point and a point I want to rotate around it. Look at this. When the pivot point is in the center, the square rotates like that. When I move the pivot, it rotates like that. So we can think of this as a line where one of its points, the vertex, is fixed and the second one is going around. We expect that the line is not going to change its length, right? We just want to rotate one point around the other. Take a look. What is happening when we do this? We are drawing a circle. That's cool, but what is it good for? Well, remember sine and cosine. Do you know what sine and cosine actually are? They literally tell you how a point travels following the path of a circle. Let our circle have a radius equal to 1. I'm measuring the angle from the axis. The x is the horizontal axis and y is the vertical axis. For the point 1, 0, the coordinates are cosine alpha, sine alpha, where alpha is equal to 0. And check this, cosine 0 is equal to 1 and sine 0 is equal to 0. What if I rotate the point 90 degrees counterclockwise? Cosine 90 is 0 and sine 90 is 1. Now, let's keep both vectors and rotate them both by an angle theta. I must do sine and cosine with respect to their adjacent respective opposite axes. So for the first vector, I have cosine theta and sine theta. But for this one, I must measure with respect to the y-axis, adjust for cosine, opposite for sine. So what happened? My horizontal coordinate is negative sine theta and the vertical one is cosine. You can see that the x-axis now has a sine component and the y-axis has a cosine component because of the rotation. To test this, I'll replace the second fixed vertex with a variable. I'll wrap it in a loop with a timer and apply the math we just derived to compute new points. Careful here. Don't edit the default points. You are computing new points by moving them every step by a higher angle. And done! Rotation is ready, so let's jump back. I need to rotate the whole square and later the cube. To make vertices cleaner, I'll use a vector or an array, it doesn't matter. I'm also going to jump one step ahead and create another array for indices. This tells us which vertices are connected to each other. For a square, I connect vertices 0, 1, 2, and 3, and assure one more connection back to 0. I'll update the loop to iterate through our vertex buffer using the index buffer. We draw a line between each pair, and boom, we have a square. Now, how do we define the vertices? In professional game dev, you choose the units you want to work with. Like 1 unit in your world will be equal to 1 meter in the real world. We are going to do it differently and define the cube in screen coordinates instead. Let's say that each face is 100 by 100 pixels. For rotation, I want the square and the cube to spin around its own center. So I'll define my vertices relative to a virtual pivot point right in the middle of them. Good, but if I try to draw this directly, the program might crash, or not, depending on your backend. I don't actually want to draw using negative coordinates, I just want to compute with them. To fix this, I'll virtually shift the origin and add an offset to all my vertices at the very end. Looking good. Let me define the rest of the cube, setting up its vertices and edges in the index buffer. But wait, something is missing, and that something is the z coordinate. Without it, I cannot create a backface, or really any other face, because I need a mechanism to physically push things further into the distance. Once we understand the principle, adding z becomes pretty straightforward, but that is not all. Our rotation formula knows nothing about z. Don't panic. 3D rotation isn't some new scary math. It's actually just 3 2D rotations stacked on top of each other. Think about the rotation we just did with x and y. We were spinning the square on the screen, right? Effectively, we were rotating it around the z-axis, which points straight out of the monitor at you. During that rotation, z didn't change, only x and y did. So to rotate the cube in 3D, we just apply the exact same sine and cosine trick to the other pairs. If I want to rotate the cube around the y-axis, like a spinning top, my height, y, doesn't change. I'm only moving in width and depth. So I just take my x and z coordinates and plug them into our formula. X gets the cosine, z gets the sine, and y stays frozen. And if I want to tumble the cube forward, rotating around the x-axis, my x stays the same and I apply the rotation to y and z. It is literally the same code, just with different variables. By combining these, we can rotate the cube in any direction we want. Before we move on, let me change my square to use actual triangles. I will change the index buffer to accept groups of 3 vertices, where each group represents one triangle. Now I will draw a filled triangle with wireframe lines over it to see it clearly. We need to define the rest of our cube. Take a look at this. I need 8 vertices and I will index them like this. We already have the front face in our index buffer, so let me add the rest. It is super easy, just follow the indices to create the triangles one by one. I also need to change my 2D coordinates to 3D coordinates to capture the z value. Remember, we need to work with depth if we are trying to achieve 3D. For rotations, I'm going to apply the formulas we derived directly, but in real-life graphics programming, we would use matrices here. I will leave a playlist with videos about 3D graphics, linear algebra, and more related topics in the description. When I let my cube rotate around the y-axis, something weird happens. It might be difficult to see, so let me use a different color for each wall, like matching a real Rubik's Cube. Now, it's clear that some of the triangles, which should be in the back, are actually clipping to the front. Why is this happening? Well, our solution currently doesn't consider drawing order, and the computer by itself has no idea what is in front and back. Fortunately, the fix is easy. It is important to define our triangles in the same manner, either all of them clockwise or all counterclockwise. We are going to use counterclockwise here. To visualize this, just take your right hand, point your thumb towards yourself, and virtually curl your fingers around the vertices. This tells you the order in which to define the triangles. For the geometry which is hidden from you, point your thumb the opposite direction. The second step is to compute a perpendicular vector to each face. We call this the normal vector. I have a video about normals if you want to dig deeper, but for now, it is enough to know that you can compute them using the cross product. If the z component of the normal is positive, it means we can see the triangle. We draw it. If not, the face is turned away from us, so we skip it. This algorithm is called backface culling. And by the way, the thumb of the right hand in our visualization represented the normal vector. Things look way better now, but something is still fishy. I will rotate the cube like that and compare it with my real cube. Something is off. And that something is perspective. But wait, there is another issue. The colors don't match. The problem here is that in math and in our thinking, we treated increasing y as going up, but in computer graphics, screen coordinates start at the top, so y actually goes down. The easiest thing we can do right now is simply switch the colors of the top and bottom faces and we are good to go. Because I'm about to add another operation, perspective, I will move my cube back to its origin. However, to apply perspective properly, I should first position the cube a little bit further away from the camera. This is important because perspective depends on position, and I don't want the camera to be sitting inside the center of the cube. The math behind this is actually quite easy. Putting into words what we want to achieve. The further the triangle, or any plane really, is from the camera, the smaller it should appear. I can do this using division, like this. My z-axis is what determines the depth, so I'm going to use that. I'll also introduce a perspective coefficient. In a professional setting, we would use more variables like field of view and aspect ratio to customize the computation. And we would definitely use matrices. But right now, we are keeping things simple to focus on the principles. And here we are. Our cube looks great. Our code is nice and tidy, and the math is solid. Now, it is your turn. All you really need are draw line and fill triangle. You can program those yourself, but if you need inspiration, here is a similar project in C++. It is very close to what we work on today, but it runs completely in text mode. As for filled triangles, we will take a look at that in the future. So if you want to see more, don't forget to hit the subscribe button. Thanks for watching, and ciao!